Hello everyone. So sorry for slight delays, but I think I'm ready now. I say in advance that today there will be no Kahoot because I think the topic is too difficult to understand right away, and Kahoot would be just a guessing game. So maybe let's do the Kahoot tomorrow at some time, so you have some time to prepare, because really the results would be terrible, because this will be probably the hardest lesson of this bootcamp, one of the harder lessons, because I'll talk about really advanced topics, specifically about covariance and contravariance eventually. So, and sorry, I have one monitor at the moment, so it's a bit tricky to manage, but I hope we'll succeed. I cannot see chat, so I also don't know how I'll handle that. But we'll see. Okay. Actually, let me open Twitch on my phone so I can see myself. So I can read the chat from phone then, because my other monitor broke. Second. Twitch. Where's Twitch? Okay, great. I see the chat now. I hope. So all should be well. Type something just for a test so I know it works, please. So today we'll talk about generics. Thanks, it works. So today we'll talk about generics, about what are they in general, where are they used to, when to use them, and when you should avoid them. So all about generics, literally all that there is in C#. And we'll talk about covariance and contravariance, and also about maker interface. So let's get to it. Start from the basics. What does generic mean? It simply means that we can, regardless of type, work with something in a generic way. So in this example, we say that a function add takes any item. So we can add any item using this method. So here you can see example. It takes an integer, a string, and an object. All the different types. Very convenient to use. So this might be very similar to what you already know about a list, because a list, you don't have integers list, you don't have objects list, you don't have strings list, you just have a list, which is generic. So that's what's under the hood. However, this method is not what list has. List has non-generic add. Why is that? Because list is a generic data structure. So a data structure that is generic always accepts the same type of T upon its initialization. That is the difference between a method, because method, every time you pass it, it can be different T's. But for something that you initialize with a specific t, it always has to be the same. So in this case, we have a creator interface, and if we initialize this creator with a specific t, it will only be able to create everything that is that t. For example, I create items. So I specify that item, instead of that t, I will say item. I'll show an example soon. So here is a generic class, an implementation of an interface, of that creator interface. So we have a generic class, creator t, and what this basically means is that this creator can be of any type, just like this, but it needs to implement that interface. So the interface was that iCreator returns whatever is created by the t. And this class basically does the same. So exact same syntax for class and interface. And now if I want to specify what objects I create every time, I can do that when inheriting or when creating. To show the example of creating, but you'll see some other examples. So here is how you can create something. And since today we won't have Kahoot, I'll probably just have a mix of live coding and theory all together. So let's do a demo of this one quickly. So, okay. So what I wanted to show is how do we create a generic type? How do we instantiate it? So I say creator is new, and I'll call it object creator. Objects creator. So I say creator for objects. That's literally all that there is. So now I specified that my creator will create objects. So if I say object creator create, it will now return an object because I specified what the creator creates. Right. So I can create different types of creators. Let's say employee creator. There is an employee class, just assume that there is. So creator and employee. And again, I can say create, and it will create employees. So this is how you initialize generic types. And about, yeah, this is how you initialize generic types. Back to the slides. So having nothing on generics works sometimes it doesn't. But if you don't have any restrictions to what types you can work with, it might become quite wild quite soon. So we need to have some constraints that we don't work with any type or with any kind of type. We want to work with classes, for example, instead of primitives, or we want to work with a certain interface, for example, but treat it specifically inside. So how do we add constraints? We simply say where after a generic type, after all the inheritance, after the normal type definition, and the normal type definition would be this bit. So after that, we can say where, and then we can constrain our t. So we say that t is a class. So in this case, now creator won't be an int and a string or a double. It can only be a complex type, any class pretty much. And the same constraint, well, in the same way you can apply different constraints for any interface, struct, or enum. You cannot constrain that class is an interface, but you can specify a specific interface. Like, you cannot just say interface here, but you can give it a specific interface, and it will know that that this T needs to inherit it. You also might wonder, why T? Is this some special symbol? And not really. By convention, when you pass something generic to have a distinction between normal types, you start everything with T. So like interfaces, you start everything with an I. In generics, you start everything with a T. And if there is like literally no context, you just leave it as T, because it can be anything. If you have, okay, so there is that. And you can have multiple parameters. For example, let's make something more meaningful, right? Let's say we need to make a generic adapter. And what does an adapter do? Well, it takes one, or better so, a converter, right? So what does a converter do? We convert something from to. Sorry. So it would be non-generic, but with multiple T stands for type, right? But for multiple types. So of course, okay, yeah, this one was way better as an interface. So let's make an interface for a converter. So public interface I converter. Which takes T from T2 and the method. And so I won't do anything yet. Here we have string to, I don't know, int to string converter, let's say, is I converter, which takes a int and returns a string. And let's implement it. So what happens is that we return well, let's say make it simple, to string. This is not needed, and this is not needed. I converter, what's wrong? Into string converter, public T2. Right, this can be specified as string and this can be int. Okay, and this can be just a one-liner. So here's an example for a simple converter, which converts integer to string. Pretty meaningless, you wouldn't do this in practice, but just showcasing the syntax that you would apply for generics. And that you basically have a single interface and not multiple interfaces per each converter. So there's that benefit. And demonstrated that you can have multiple generic types in a single data structure or a method. Let's go back to slides. So we have constraints. We can have different kinds of constraints. And there is one special interesting constraint called new constraint. And what new does, it basically means that something can be created, but with a default constructor. So if you're creating a factory of some sorts and you are supporting creation of objects that have no constructor and you want to do it no explicit constructor and you want to do it in a generic way, initialize them in a generic way, well, you can use that constraint and just create something that you don't know what it is, but you can create it because you constrained it with a new constraint. Please clarify your question, Aurora. I won't move to covariance and contravariance until I ask that question. I'm not sure what you mean. This works for this one as well, of course. Like, I can make an abstract class, for example, which is also with both of those constraints, which implements that interface, which also has those both constraints. Right. So the prime reason why this other thing was not so good was because it is not really sensible and logical to implement a generic converter when you cannot convert something. So from what would be the implementation of this? How do I know how to convert from one thing to another? If it's anything. Some things cannot be converted, simple as that. And therefore, I chose not to implement it through a method, but rather through a generic data structure. Because I simply don't know how to implement this method. Here, it's trivial, but here it would be very complex. No, you cannot do that. It would fail in most cases. Casting would break. Yeah. Okay. Yes. You can use as for casting and then it would be null. But again, I want to support conversion to something that doesn't have a reference to value types, and I cannot. Okay, any more questions? It's the first part of the lesson, and I would like to know if it's clear, if people understand this concept that stuff can be generic and that we can treat methods or types in a generic way. Basically, the purpose of this to work with something, treat something the same way, but that something can change. So behavior doesn't change, but the type for which you apply that behavior changes. And that is the essence of the meaning of generics. What about others? people who are new to this, I really want to know if this is clear or not, because this is considered advanced topic, and I want to make sure before we move on that you're crystal clear. So can you please answer this question? And I would like to ask everyone who's watching, can you please tell me what is the benefit of generics? Why do we use generics? So I'll give you 1 minute to answer this question. It would be a bit better if you could provide a more explicit answer. So, okay, Cat Girl said, one clear example I've seen to make data structures that can work for anything, like a list for anything or a stack for anything and so on. Yes, that's a very good example. Instead of implementing the same functionality for 10 data types, you don't have to, and you do it once with generics. Yes. Okay. I didn't see any wrong answer, so I presume this was clear. So let's move on to a more difficult topic. A very difficult topic, in fact, which is covariance and contravariance. Basically, why the lesson was delayed was because of this topic. It's so difficult because it's counterintuitive the way it works for generics. And I'll start from probably live coding example, which should make it clear. So imagine we have an interface. Let's call it the same interface, iCreator, right? And more like iBuilder. So builder can build. Out is not good. Okay, the same converter actually. Okay, yeah, converter. Converter can convert from one thing to another. T from T2. And we take this, we take that. Actually, I won't have that method. Pretend it's there. I'll just close it. And then we'll have a class. So, converter. Which is also generic. So, let's create two converters. Not good, not good. Two generic types will make it complex. I'll just call it a builder. Builder, T, whatever. So we have a builder, not the converter. Okay? And let's create two builders. Yes, it would have been. Okay, So we have iBuilder for string, and we say builder string string builder new string, and then we have another one for object builder. Now, what happens if I say generalized builder, which is iBuilder of object? And what happens if I assign it string builder? Will it work? What do you guys think? Can I assign generalized builder to, can I assign string builder to generalized builder? Just like I would, you know, have a string, an object, and then I say, I'll call it specific, I'll call this general, then I say generalized. So of course I can assign generalized something specific to something generalized. That's how programming, that's how object-oriented programming works. String derives from object, therefore I can assign string to this object, generalized. It's a generalization, therefore it works. So, however, so this is normal, this is nothing special. However, the same doesn't work for generics. If I do this, it doesn't work. And this is something counterintuitive. And I took, I think, 3 or 4 hours just making examples to make this clear and to explain why is this like this and what are the rules that you should follow. It would work the other way around. That's the point. But not in this case. In this case, it wouldn't work the other way around. It doesn't work any way around with the current thing. So if I say string, it still doesn't work, but it can work with very little effort. And if I make this in, I cannot make this an in, I can make this an out, and then this will work. So generalized. Then this works. Put it in the wrong place. Here. Confusion. I don't need it there. Okay. Oops. So yes, if I put out in there, it works. If I put in there, it can work the other way around. Again, it's repeated. Specific builder. So if I put in, I can specify. If I put out, I can generalize, which is what the hell is going on? Something is really weird, right? So let's delve into this weird behavior. If I remove this, it would not. So we have object, and if I say new builder for string, it will not work. Because it's essentially the same, like doesn't matter if you assign it at the same time as initializing or after initializing it. It's exactly the same, so it's irrelevant. So what the hell is going on? What's this behavior? And what you witnessed there is an example of variance and covariance. Sorry, covariance and contravariance. And this is something that is slightly different in generics. Sorry for not fitting everything in one slide. So let's look at another example. What you saw with so this example is actually contravariance. Well, this is actually neither. In C# terms, this is neither, but it demonstrates that the contravariance. So we have basically the same thing that I just showed. An interface. I'll show it from code. It's not the full picture. Not this one. This one. So again, we have this interface and a specific class, and we have another interface and a specific class. So the first interface is without, and the second one is within. The first interface is covariance, and the second one is contravariance. And therefore, for covariance, we can generalize the interfaces, and for contravariance, we can specify the interfaces. So here we make a generalization, and here we make it specific. And how does it work when it's specific might be the tricky bit. But there is another example that I'll show to demonstrate each with a very, very logical example. So now that we've established that generalization in generics is counterintuitive, let's continue. So covariance basically means that we are able to retain our original form. So if a string, so if something derived from something, so if child derived from parent, then that means that I can still treat child as a parent. So string derives from object, that still means I can treat string as an object. And for interface generic data types, it means that if my generic type, if my interface, if my interface or if my class, if my generic class or interface has T, which is deriving from some parent, that means that when I create two instances of that class, generic class, if one instance had child T and another instance had parent T when creating it from, that means that I can store both or treat both as a generalized T. So in the case that we showed here, that would be I created a string, so a generic for string a generic for object, and that means that I can treat a generic for string as generic for object. And why is this possible? This is possible because of out keyword. So if I don't put any keyword, any modifier next to t, it means that I can neither specify nor generalize it. And in this case, I can generalize it. I created a specific covariance or any other class that is generic. And then I created a more general class that is generic of object. And this means that I can then store both as generalized forms. Now, questions. Does the out and in work in similar way as when we did it in out and ref? And the answer is no. They are absolutely unrelated and they shouldn't be mixed. This out and in means exactly completely different things. So it's important not to mix the two. All right. So out, again, out means something that we can generalize. If I created a generic without t, that means I can generalize it. You will understand because now it's just to illustrate the syntax and the concept rather than have a meaningful example. There is a good example that will be coming soon. Okay. So the opposite of covariance is contravariance. And it basically means that we can specify instead of generalize. We can specify a type for a parent. Instead of generalizing a child to a parent, we specify a parent to a child. So stuff can be specified. Yes, without you can go from child to parent. Exactly. And from in you can go from parent to child. Yes. So within we specify contravariance. And this one is the counterintuitive one because normally in polymorphism we cannot say that a generalized type is something specific. Like it doesn't work that way. We can cast it and it might work based on the initial type, but for generics it will always work, and we'll find out why. And very simple rules when to use what. So if you have output, if your generic returns something, use out. If your generic inputs something, use in. And don't use any generic if you have both. That's basic rules that you should follow. Very simple. For every input, add in, and for every output, add out. Very simple rules for generic. Covariance and contravariance. So, how to remember the names? The more simple word is covariance, and being the more simple, it's more intuitive as well, because it's based on polymorphism, something that's very natural to object-oriented programming. Contravariance is the opposite, therefore you have contra for the name, like the opposite. So for contravariance, we can only consume output right. So explaining again the two, for out, it means we can consume output polymorphically, and for in, we means that we cannot consume input polymorphically, but we can consume it specifically. Very confusing, I know. So soon, now the example that should hit the nail. Took me very long time to make. Okay, so let's start with the easy one, covariance. Let's first see the context. The context is this: we have employees, different kinds of employees. So a base employee class. So every employee has an ID. You can either assign it during creation, or you can just let it generate itself. And employee does work. And then you have many specified employees. They probably would have their own work implementation, but it really doesn't matter. It doesn't matter to the point. So you just have different kind of employees: janitor, programmer, game dev, backend dev, and full stack dev. And by the way, those three, the last three, are programmers. So the last three are programmers. So we have a bunch of employees, and some employees are programmers. And we have a workplace. And workplace basically means that we can give it a GUID, which is an employee ID, and get employee by its ID. So we pass a GUID, an ID, and return an employee. Since we return an employee, it's without modifier. And we added a constraint. Our generic is not everything. For example, we don't return ints or objects or strings. We only return employees. So this is a covariance because it's out. Because whatever we retrieve, we might want to generalize. We retrieve employee, a specific employee, but we want to generalize it to just an employee, maybe. So we have a division. So workplace works for all employees. However, division might not. And we have specialized divisions. We have an abstract class for division, which basically says that for whatever employees I have, I can get them by their ID. So it's just a for each loop, which checks if employee IDs match in the list of employees that are in a division. And if they match, I just return an employee. I don't know why it's F. I'll refactor employee. Yes, programmer is a specific type for employee. So you have this function, which is implementation for the interface. To get an employee by the abstract class, nothing that interesting. And now we have specific divisions. So a division for full stack developers is basically a division for full stack dev. A division for game developers is a division for game dev. And programmer division is a division for programmer. I think this is very readable and intuitive, and it's just a good example. So the question, what does division add do? Division add does exactly the same as workplace add. Oh, sorry, division add. Ignore this for now. Should you ignore this for now? Ignore this for now. Ignore this global division. So we just have 3 divisions: full stack division, game devs division, and programmers division. This one you don't know about yet. I'll explain it soon. T employee is a generic type. Why not use just a workplace? I didn't use just a workplace because a workplace, I think, to me, workplace logically means the whole company. And the whole company has different types of employees. However, division is a specialized section in the company that works with specific employees. So workplace could be just, the whole company X could be a workplace. However, there are many divisions in a company that it has. And actually, this should have been a workplace for programmers. Yeah. So ignore that one for now. Yes, so these are divisions, and workplace itself is made of many divisions. I'll call it workplace. Let's say Square Enix company. The Square Enix company has programmers, game, and full stack divisions. Ignore that for now. And the demo. So this bit we don't need yet. Okay. So we have 3 divisions created: programmers division, full stack division, and game division. And since it's covariance, that means that we can store all divisions into a generalized form of T. So we can say that all divisions are there. This division, and this division are all divisions, right? So they're there. And this works. So this is intuitive and normal, and all is good. Let's delete this. Now let's move on to a bit more details. So we also have a workplace, and a workplace is made of many divisions. And you register a division. Probably it makes more sense. Yeah, you register a division like this. So this workplace contains only divisions for programmers. And the whole point of this is that in a workplace, I can still, just like in a division, find employees. But finding an employee in a workplace, such big workplace like Square Enix, would mean looking for the employee throughout all of divisions. So I call each division's getEmployeeById, and I then return it if it's not null, if it was found. So you have multiple divisions, and you get you check if employee exists in each division. And if it exists, you return it. So this is a find in a workplace, employee search in a workplace, and this is an employee search in a division. So here I just check if IDs match, and here I check if it was found. That's all. Just call basically that method for all the divisions and get it. Do you have any questions on how a workplace like Square Enix works? I think this should make sense. So you have a workplace, and the key point here is that regardless of having different employees in different divisions, or rather different programmers, I can still get them as a generalized type. So I get employee by ID, and that employee that I retrieved is a generalized programmer. So this is the example that is more simple and more clear. Now let's move on to contravariance, something that is not intuitive. So we have a bunch of managers. And what do managers do? They manage people. They manage employees, in fact. So we have a manager, and a manager is specialized. Like, we don't want manager to manage anyone. We want it to be per division. So we add a constraint that maybe we'll want to manage only specific kinds of employees, right? So we have a general employee manager, which can manage every employee. And then we have specialized managers, like programmers manager, like janitors manager. So employee manager says, do work in general, and then just asks an employee to work. Programmers manager says, do programming, and then asks employee to work. And janitor's manager says, do cleaning, and then asks employee to work. So it's very simple classes, nothing special there. The key point is that it's contravariant. Contravariant because employee goes as input. So again, quite simple and quite simple classes. But the way we treat them polymorphically is not so simple. So let's move on to a demo, and I added a bunch of comments there. So just like for divisions, we create 3 types of managers. We create janitor's manager, programmer's manager, and employee manager. Employees manager, actually. So we have 3 kinds of managers. And now let's just hide everything, and let's get that counterintuitive example. If I have a manager of employees, if it was a covariant, something like this would work. However, it's contravariant, and therefore it doesn't work. Managers. So it's contravariant and it doesn't work, right? Counterintuitive, because you might think that since janitor and programmer are employees, then iManager employee should be able to take all those managers, but it cannot. Now let's delve into why. So employee manager is not janitor's manager. However, both work if we... Okay, so let's think what would happen. Let's go back to that example, the one that didn't work. So imagine this is valid, okay? And imagine we are, so we have a manager, right? And we say for each manager, which is manager, employee, and we say manager, manage, and I create a new employee, which is a janitor. Let it sink to you. Look at this for each and let it sink to you. So we have different employees like janitor, programmer, and employee, and we do a for each loop. However, regardless of having different employees, we pass in a janitor. Well, of course it won't work, because a programmer will not be able to handle a janitor. Programmer's manager will not handle janitors. Only those two are valid. So let it sink to you. Programmer's manager cannot handle janitors. Therefore, programmer's manager cannot be generalized as manager for employee, because it's not. It manages programmers. So programmer's manager cannot manage janitors. Employee's manager, however, can manage janitors. Think about it. Yes, janitor and programmer both inherit from employee. So think about this again. Managers that are generalized cannot treat specific employees because they might not be able to handle them. Like janitor doesn't handle programmers and programmer doesn't handle janitors. However, employees manager handles both just fine. So how does this work? So in contravariance, everything is opposite. We have a manager, so we can specify that employees manager will be manager janitor. And what this actually means is that employees manager will simply accept janitors as input. That's all it means. So janitors manager accepts janitors as input. Employees manager accepts also janitors as input. Since janitor is an employee, it simply works. This doesn't mean that that employees manager will suddenly behave as manager for janitors. It simply means that it handles janitors as well as other employees. That's all it means. The specification of type only applies for input in contravariance and only for output in covariance. Well, for output and the whole type as well. So for contravariance, it applies only for input. So we have managers which are specified for janitors. All right, so what does this mean? This means that all those managers that we have works with janitors because it says so in the type. And if I run this example, which is a contravariance example, you will see that based on the code, first one was janitors, second one was employees. And so you see do cleaning, which is what janitor's manager says, and then the employee does the work. And then we say do work in general, which is what the employee's manager says. Right, so I definitely agree that's the confusing part. So again, you should try to think a bit differently because this is not a typical object-oriented programming situation. The question was how can iManager for janitor handle iManager for employee? And the answer is iManager for janitor doesn't handle iManager for employee. This, what I just wrote, doesn't mean that I generalize managers. It means that I generalize input. It means that both employees manager and janitors manager can handle janitors. This is all that it means. Generalization of input, not generalization of managers. More like specification of input, to be precise. And of course, it doesn't manage all employees. If I say employee here, you see, it doesn't work. Now, why doesn't this work? Can you guys explain? Why doesn't this work? Why can't I just